Hello and welcome to Bitcoin Explained, where I break down some of the more technical aspects of Bitcoin in a simple way. Now this video is actually the first in a 5-part series on the cryptography behind Bitcoin. The cryptography behind Bitcoin is one of those technical aspects that a lot of people unfortunately never bother to understand because it simply sounds too complicated. But as I will show you in this video and all of the following videos, it doesn't need to be that way. You really only need to understand high school level math and have the ability to think abstractly. And in my opinion, anybody who can do those two things can understand cryptography. I will be walking you through real life examples, explaining everything as simple as I can and showing you really helpful visualizations along the way. Now with all that said, let's talk about why cryptography is important, and then we'll talk about finite fields, the topic of this video. Enjoy. Before I start talking about finite fields, which is the topic of this video, let's actually put cryptography as a whole into perspective and look at why it is so important, especially to Bitcoin. Now, in Bitcoin, elliptic curve cryptography is really at the heart of Bitcoin transactions. It's what allows participants in the Bitcoin network to sign a transaction with their private key, and then anybody else in the network can verify that the transaction was signed by the owner of the private key without ever revealing those private keys using the public key. Now, this is possible thanks to some clever cryptographic principles and a little bit of abstract mathematics, which is what I'll be teaching you about in this video and the next video. The term elliptic curve cryptography might sound a bit scary at first, but the underlying math really isn't that complicated. The only two fields of abstract mathematics that you need to understand in order to be able to understand cryptography are what's called finite fields, which I'll be talking about in this video, and elliptic curves. Once you understand those two fields of abstract mathematics, you can combine the two to get elliptic curves over finite fields and then move on to elliptic curve cryptography. From this point, it's only a small step to understanding the elliptic curve that Bitcoin uses and how the signing and verification algorithm works from a deep foundational technical level. As I said in the introduction of this video, there will be 5 videos on the cryptography behind Bitcoin. This video, video number 1, is focused on finite fields. In the next video, I'll be teaching you about elliptic curves over real numbers. In video number 3, I'll be teaching you about elliptic curves over finite fields, so combining the first two. And then we'll move on to Bitcoin's curve, so the elliptic curve that Bitcoin uses, which has specific parameters. This will be easy for you to understand once you understand the topic covered in video number 3. And then finally, once we have all of the pieces to the puzzle, we'll move on to elliptic curve cryptography and the elliptic curve digital signature algorithm, ECDSA for short. This is just the cryptographic signature scheme used in Bitcoin, and it's really where the magic happens. So you want to get to this point, because once you get to this point, you understand everything about elliptic curve cryptography and how signatures in Bitcoin actually work. Okay, with all that said, let's talk about finite fields. So a finite field is just an algebraic structure with a finite number of elements. And as you can see on the screen here, this is usually denoted using a capital F and P. P is the order of the finite field, which just means how many elements are in the finite field. And there are a lot of different types of finite fields, but by far the most common one, and the one that we care about in Bitcoin's case as well, is what's called integers modulo a prime number p, meaning that this number p here, in our case, always has to be prime. So the number of elements in the finite field are prime. In this example, you can see that it always starts with 0 and then increases by 1 all the way to p minus 1. This is p minus 1 because we start with 0. So if we have a finite field of order 29, for example, which is a prime order, then this would be the values 0 all the way to 28. So in these finite fields, you don't have any negative values and you only have integer values. This is really similar to how real numbers work. The only difference is that we don't have negative values and we don't allow any fractions or irrational values, essentially. Now, unlike the familiar field of real numbers, finite fields, because they have this limited number of elements, have some properties that are really intriguing and make them perfect for cryptographic applications. You'll understand this later on in this video. Now, what can we actually do with elements in a finite field? So here I've got an example finite field, the one I just mentioned, of order 29, which has all of the elements from 0, or the integers from 0 to 28. With finite field elements, we can do 4 operations. Those are addition and subtraction, multiplication, and division. Now, the interesting thing about finite fields is that each of these operations on a finite field element or between two finite field elements leads to another element also in the finite field, making it a closed system. But now, if you actually think about that, this might seem a bit odd to you because, for example, we could choose 2 numbers that are contained in this finite field, let's say 20 and 25, which clearly are integer values in this finite field. And if we then do addition, which is one of the operations that we supposedly can do on finite field elements, then how does that result in another element that's also in the same finite field? Because 20 plus 25 is equal to 45. How does this work? This is where something called modular arithmetic comes in. And this is where the abstract mathematics comes in a little bit as well, because in abstract math, such as finite fields, we can actually define operations in any way that we like, as long as they adhere to certain properties, which we'll learn about in a second. So before we move on to the properties, let's actually talk about what modular arithmetic, also known as clock math, is. For those of you that have done some programming, you might be familiar with this already, because the modulo operation is really commonly used in programming in order to create cyclical patterns or do time calculations. Now, in order to explain this, for those of you that don't know how this works, we'll actually first be looking at an analog clock, because this is called clock math after all. Then we'll look at integer division and the components of it that you all should know from high school mathematics. And then we'll look at some real-life examples using finite fields. Now, why is this called clock math? If you look at this analog clock, and I hope that all of you can still read this, I know that it's becoming less and less common nowadays to be able to read analog clocks, but I still come from a generation where that was very much common to be able to do. What we have here is we have the second hand as the red hand here, then we have the minute hand, which is pointing to 12, and the hour hand, which is pointing to 2. Now, let's not think about the second and the minute hand in this case, and only look at the hour hand. Just from looking at this analog clock, you can tell that it's 2 o'clock, but you can't actually tell whether it's the second hour of the day or the 14th hour of the day, because a day has 24 hours, but an analog clock only can represent 12-hour values. So technically, just by looking at this, you wouldn't be able to say whether it's 2 a.m. or 2 p.m. And the reason for that is, like I said, that after you get to 12 on the hour hand, it wraps around and starts again, technically at 0, and then the next value is 1. This is really similar to what we want to do with modular arithmetic. So let's keep this concept in mind and look at how integer division actually works. So if you have 2 integer values, a and b, and you divide a by b, then what you get is what's called q, the quotient, and the remainder r. Now, let's look at a really simple example and take the number 3, which is a prime number. If we then take all of the values that we would typically see in a finite field, 0, 1, 2, and so on, and divide them by 3, then we get the following pattern. So 0 divided by 3 is equal to 0 with the remainder of 0, obvious. 1 divided by 3 is also equal to a quotient of 0 with the remainder of 1. 2 divided by 3, 0 with a remainder of 2, And then as soon as we get to 3 divided by 3, we get a quotient of 1 with a remainder of 0, because 3 fits into 3 ones with nothing left. It fits into 3 perfectly, so to say. Then when we get to 4, we get a quotient of 1 with a remainder of 1, because 3 fits into 4 ones, and then we still need to add 1 to it in order to get to 4. And then when we look at 5 divided by 3, we get 1 with a remainder of 2. Now in modular arithmetic, all that we care about is the remainder. And if we only look at the remainder, we can identify a pattern here. Now for the first division with 0, this is 0, then it's 1, then 2, and then the next number in the pattern should be 3, because this is just increasing by 1. But because 3 is the number that we're dividing by, as soon as we get to 3, we wrap around to 0 and then start again. 1, 2, and then if we did 6 divided by 3, the remainder would be 0 once again. This is similar to how in clock math, once you get to 12, you wrap around and then start again at 0 technically, and then get to 1 as the next hour hand. Which is why if we did this modular arithmetic using 12, for example, the 14th hour of the day would be equal to 2, in the sense that 14 divided by 12 is equal to 1 with a remainder of 2. And 2 divided by 12 is equal to 0 with a remainder of 2. So when we do modular arithmetic, 14 and 2 become in a sense equal to each other. Okay, that's interesting. Now let's look at a real-life finite field, the one that we looked at before, the finite field of order 29, with all the elements from 0 to 28. So when we then actually do the addition that I talked about earlier on elements of this finite field here, 20 and 25, the way that we ensure that the result of this addition is another element that falls in the same finite field is by computing it modulo 29. This symbol here, the percentage sign, indicates that we're doing a modulo operation. And what that just means is that the result of this operation, or all that we care about in this operation, is doing the division and then getting the remainder. Meaning that if we add 20 to 25, we get 45. If we then divide that by 29, we get 1, the quotient, with a remainder of 16. Now you can see there's a triple equal sign here. This is what's usually used in modular arithmetic to symbolize what's called congruency. Now we don't use equality in this case because there isn't really such a thing as equality in finite field elements. This will become clear when we look at the next addition. So we could, for example, do another addition, which is adding 54 to 20 instead of 25, and then computing it modulo 29, which would also give us 16. Now, the reason why this is the case is pretty obvious. It's that 54 is actually 29 higher than 25. So when we compute the remainder after dividing by 29, then the remainder will be the same because we have this cyclical pattern. But that's why there's no equality, there's just congruency. Another way that you can think about that is that what we basically do with modular arithmetic on finite fields is that we take any integer values that fall outside of the range of these acceptable values here. So when it basically overflows at 28, then we always wrap around to get another element. But what that does is it slices all of the integers that are a result of addition, multiplication, or other operations that is higher than 28. It slices that into one of the slices of this finite field, which are just 29 different slices or elements, 0 to 28. And then there's a lot of different elements that are congruent to these numbers as you take the integers higher and higher and higher. So any almost infinite amount of integers could be converted into one of these finite field elements by doing modulo 29 and then finding the remainder, or what that is congruent to. That's just what this means. Now, a finite field needs to have certain properties. Let's have a look at the 6 properties that a finite field needs to have, and then we'll talk about each of them in great detail. So the 6 properties that a finite field needs to satisfy, or that the finite field elements need to abide by are, first of all, closure. This means that if an element A and another element B are in the set or in the finite field, then A plus B and A times B must also be in the set. Associativity means that it doesn't matter how you group the operation, the result will be the same. So if you first do A plus B and then add C, the result should be the same as first doing B plus C and then adding that to A, and the same for multiplication. Commutativity just means that the order of the operation or the order of the elements in an operation doesn't matter. So A plus B should be the same as B plus A, same for multiplication. Distributivity means that multiplication distributes over addition. So if you have B plus C in the brackets here and multiply that by A, then you can distribute the multiplication out. The fifth property is identity elements. So for finite field elements, there also need to be two identity elements. One for addition, which is 0, and one for multiplication, which is 1. Then lastly, there also need to be inverses. So every non-zero element has a multiplicative inverse, and every element has an additive inverse. Let's look at each of these in detail. Okay, closure. As we said, if A and B are in the set, then A plus B as well as A times B should also be in the set. I've already proved this with addition in the example earlier, but let's look at the same finite field of order 29 for multiplication. If we take two elements that fall in this finite field, 3 and 20 for example, then how do we make sure that the result of that multiplication also falls in the finite field? Well, once again, we basically just compute the result of that operation the way that we do in normal math as well. So 3 times 20 is equal to 60, and then compute modulo 29. Again, just divide by 29 and get the remainder. Now 60 divided by 29 is equal to 2, because 2 times 29 is 58, with the remainder of 2, because it takes 2 more to get from 58 to 60. The interesting thing is that modular arithmetic is able to wrap around and put elements back into the finite field even if they are negative values. So within the finite field, we're not allowed to have negative values. But if through an operation we get to a negative value, then the modulo will get that back into one of the elements in the finite field. Now an example for this is if we take 10 and 25, which are both elements of this finite field, and we subtract 25 from 10, that's minus 15. Modulo 29, that is congruent to 14 actually. So what that means is that we're not just able to wrap around the edges of this finite field when we overflow past 28, where we start again at 0, but the same thing happens when we go below 0. So if we go below 0, in a sense, we wrap around the other side and then keep going back down as many elements as we still need to subtract, and in this case that would be 14. Now to understand this, there's two different ways to think about this. So 10 minus 25 is minus 15, which is 14 away from minus 29, but you can also think about this as wrapping around after 0 and going to 28 and then still having to deduct the other 15 from 29, which gets you to 14. So even negative values or the result of subtraction or multiplication that results in a negative value is able to be sliced into one of these finite field elements. Associativity, once again, this just means that the way in which elements are grouped in operations does not change the result. If we take the same finite field, for example, and we do 10 plus 44 first and then add 20 to that, modulo 29, that's congruent to 16. The same happens if we first do 44 plus 20 and then add that to 10, modulo 29, also congruent to 16. This is just exactly the same as in regular math and should be pretty clear. Commutativity should be even more clear. That just means if you do, for example, 11 plus 20 modulo 29 it's the same as doing 20 plus 11 modulo 29. Both of these are equal to 31, which divided by 29 leaves a remainder of 2. Distributivity is also the same as it is in normal math. So if we take a different finite field, just to switch it up a little bit, of order 23 with all the elements 0 to 22, and we multiply 10 by 12 plus 15, modulo 23, that's congruent to 17. Now that is exactly the same result as distributing the 10 out over each of the components within the brackets here. Both of these are equal to 270, which is divisible by 23 11 times with a remainder of 17. Identity elements, now this just means that for addition there's an additive identity element, 0. This is also the same as it is in normal math. That just means that an identity element just means that if you do an operation with the identity element of that operation, so the additive identity element for addition and the multiplicative identity element for multiplication, the element remains unchanged. So for addition, this essentially just means that if you have an element 5 and you add 0, then the element remains unchanged. So 5 plus 0 is just equal to 5, just like in normal math. For multiplication, this just means that if you multiply 5 by 1, you still get 5 and the element stays the same. Inverses mean that every non-zero element has a multiplicative inverse and every element has an additive inverse. So if we look at the same finite field of order 29, 0 through to 28, then what that means is that in normal math, for example, the additive inverse of a number would be the negative of that number. So for 15, that would be minus 15. For finite fields, this is similar but a little bit different. It's just the number that's congruent to the negative of that number, meaning that as we saw before, 10 minus 25 in the finite field of order 29 is congruent to 14, which is minus 15 modulo 29. And then if we add 14 and 15 in this finite field, modulo 29, sorry, this should be a 0 here, it's not 14, that gives us 0, meaning that an additive inverse of any element is the element that when added to the original element itself results in 0. Just like in normal math, when you add 15 and minus 15, you also get 0. Now the multiplicative inverse of a non-zero finite field element is probably the most difficult concept to grasp about finite fields, but it's super essential to understand because it's what makes finite fields actually a closed system. Now, before we move on to finite field division and the multiplicative inverse, let's have a look at why P, so the order of the finite field, actually has to be prime. Why is it so important for the security of cryptography and especially the cryptography in Bitcoin that the finite field has a prime number of element and not any other number? In order to explain this, I'll be walking you through a thought experiment, which is the following. If we have a set in finite field of order 23, for example, that looks like this, which is x multiplied by 0, x multiplied by 1, x multiplied by 2, and so on until we get to x multiplied by p minus 1. So essentially just x multiplied by each element of that finite field for a variety of different x values, let's say 1, 2, 7, 11, and 14, then what does the resulting set look like? Now I've written some Python code just to loop over the different x values and to print the results because it makes this easier. But basically what that looks like is all of these lists that I'm printing out here. Now it's a bit hard to see because the numbers aren't all in the same order, but all of these lists have a length of 22, so p minus 1, and they actually contain all of the elements from 0 to 22 only once. So basically all of the elements that are contained in the lists here are still the original elements from the finite field, just in a different order. If we sort these lists when we print them, this becomes really clear. Now, an interesting fact about that is that the x values don't actually have to be less than p. So even if we use x35 as the last value to iterate over to create this last list here, we still end up with the same sorted list. Now the reason for that is that we compute everything modulo 23 in this case. So it doesn't matter what number we have here, even if it's higher than 23, because we do modulo 23, everything gets divided by 23 and we only get left with the remainder. What happens if p is not a prime number? So in this example, I'm using p equal to 14 instead of 23, which was a prime number, and 14 obviously is not prime. If we use the same axis as we used before and create the list, then one thing we can see is that while all of these lists are still 14 elements long, only the first list contains all of the original elements that should be in the finite field, which are the values 0 through to 13. In the second list, we can see there's a lot of duplicate values. We've got 2 zeros, 2 fours, 2 sixes, and so on. In the third list, it gets even worse. We have a lot of zeros and a lot of sevens. Now let's actually remove the duplicate values and look at only what unique values are left when we do this. What we can see here is that if we use a p that's not prime, so if the order of the finite field is not prime, then multiplication by one of the divisors will lead to a smaller set. That's also why if we multiply all of the elements in the finite field by 2, we only get left with 7 elements, because 14 divided by 2 is equal to 7. If we multiply everything by 7, we get left with only 2 elements, again because 14 divided by 7 is equal to 2. Now this is why it's so important that p is a prime number, because in Bitcoin we want to be able to multiply any of the elements in a finite field which fall on an elliptic curve in the cryptography part by any number without reducing the possible elements that we could reach through this multiplication. So when we go from a private key to a public key, we want to be able to maintain the range of full values for the security of the cryptography. Otherwise, if multiplication reduced the set of all the values that we had, the security would be compromised and somebody might be able to backsolve for your private key, thereby being able to steal your Bitcoin. This is only not the case and only guaranteed not to be the case if we have a prime order. That's why it's so important that p is prime. Now, before I move on, I want to quickly highlight one thing. So I've created a whole Python class for finite field mathematics, and everything else I'll be talking about in this tutorial series. So elliptic curves and elliptic curve cryptography as well. I'll be linking to the GitHub repository to the code in the description of this video. Anybody with some programming skills, especially with Python, feel free to check it out and play around with it. It makes all of this a lot easier. And if you play around with it, you tend to understand things a lot better. But now let's move on to finite field division and dive deep into that. Before we talk about how the division works, we need to understand what a multiplicative inverse actually is, because that's what we will end up using in order to do the division. So in regular mathematics, multiplying by an element by its multiplicative inverse should be equal to 1. So basically, if you have 6 in normal math and you multiply by the multiplicative inverse, which in normal math is just the reciprocal, which is 1 over that number, then you multiply 6 times 1 over 6 and you get 1. Now, in finite fields, once again, the logic behind this is really the same. So the multiplicative inverse should be the number that when you multiply it with the element that it's the inverse of results in 1. But here it's not as straightforward as in normal math because we can't use fractions. So if we look at an example in the finite field of order 23, the number 7, what would be the inverse of that in this finite field? So the number that when multiplied by 7 results in 1. Remember that we do everything modulo 23 here, so we have to find the number that when we multiply 7 by it and then divide by 23, the remainder is equal to 1. If we do trial and error, for example, we could loop over every element in this finite field, multiply it by 7, compute it modulo 23 and see whether the remainder is actually equal to 1. For this finite field, because we only have 23 elements, that's pretty straightforward. but for a finite field with a way larger order in the billions, trillions, or even higher, this would become computationally infeasible at some point, and you wouldn't be able to do it. So how do we do it then? First of all, let's look at the proof of why 10 is the correct value for 7, and then we'll talk about that. So 10 is actually the correct value here, because when you multiply 7 by 10, you get 70, and then if you divide that by 23, you get a remainder of 1, because 23 times 3 is equal to 69, which only leaves 1 to get to 70. So in this finite field of order 23, the number 10 is the multiplicative inverse of the number 7, meaning when you multiply them together, you get the number 1. This is sort of how 1 over 6 is the multiplicative inverse of 6 in normal mathematics. Okay, now that we understand what a multiplicative inverse of a finite field element is, we only need to understand one other component in order to get to finite field division, which is a mathematical theorem called Fermat's little theorem. Now, the derivation and proof of this in terms of the mathematics is way beyond the scope of this video, but for anybody that's interested, I'll be linking to a really good YouTube video that explains all of this in detail in the description below. You just need to understand that it is the way that it is, and I'll prove it to you using code and an example, but you just need to follow along and understand this. So Fermat's little theorem just states that for any integer m that's greater than 0 and less than p, where p is prime. Remember, p in our finite fields, the order of the finite fields is always prime as well. We get the following. That integer to the power of p minus 1 modulo p is congruent to 1. And this will always be the case, no matter which of the integers, which of the elements of the finite field you choose. If you raise it to the power of p minus 1, so the order of the field minus 1, modulo p, the order of the field, that is congruent to 1. Now, the way that we can justify this is by using some examples and printing it out and seeing whether this is actually the case. And then we just have to trust that the proof and the mathematics is correct, but I checked it out and trust me, it is. And you won't be able to find an example using the code I'm about to show you that disproves this. So to justify that, we can look at the following case, which is just computing this set here. So 1, 2, 3, all the way to p minus 1, all raised to the power of p minus 1 in a finite field, so doing everything modulo p. So we're just taking all the elements in a finite field except from 0 and doing exactly this up here. Now I'm choosing a variety of p values, 3, 7, 11, and 29, all prime numbers, and printing this out. Once again, some Python code here. This will also be in the GitHub, so if anybody wants to play around with other p-values, feel free to do so. You will get exactly the same result. If we print the resulting set of doing any of the values in here, raising x in the range of 1 to p to the power of p minus 1 modulo p, so just doing what we saw here for any of these values, then the resulting list is always a list of ones. So the result is always 1. This just proves that any element greater than 0 and less than or equal to p is congruent to 1 when raised to the power of p minus 1 modulo p. Now, why do we care about this? How is this important in finite field division? And how do we use this? So for finite field division, we'll once again rely on similarities to regular mathematics. In regular division, which can be rewritten as a multiplication by the reciprocal, so 6 over 2 becomes 6 multiplied by 1 over 2, the reciprocal of 2, which is equal to 3. Dividing by a finite field element can also be rewritten as multiplying by the multiplicative inverse of that element. And if you write that down formally, what that looks like is if we have two finite field elements, x and y, then we can rewrite the division x divided by y as x multiplied by y to the power of minus 1. So the inverse of y. Earlier we saw that for small finite fields it's easy to find the multiplicative inverse of an element through trial and error, but how do we actually get this value for a really large finite field where we can't possibly loop over every element until we find the one that multiplied by an element gives us 1. That's where we use Fermat's little theorem. So remember that from Fermat's little theorem we have that any element raised to the power of p minus 1 modulo p is congruent to 1. Which means that we can rewrite y to the power of minus 1, so the inverse of y, as y to the power of minus 1 multiplied by y to the power of p minus 1. Because any y that's greater than 0 modulo p will be congruent to 1. So if we multiply an element by something that's congruent to 1, then that element should remain unchanged. But the interesting thing about this now is that we can group these exponents of y, p minus 1 and minus 1, as y to the power of p minus 2. So in the end, the division x divided by y then just becomes x multiplied by y to the power of p minus 2. Now this is way easier because we don't actually need to figure out what the inverse is in a trial and error brute force looping through every number type of way, but we just take y, so the original element that we want to divide by, raise it to the power of p minus 2, which is also known because we know the order of the finite field, and that then becomes our division, or our multiplicative inverse for that matter. So if we look at an actual example of the finite field of order 23 again, we have all the elements from 0 to 22 as we saw previously, and we, for example, know that 10 is the multiplicative inverse of 7. How would we prove this using Fermat's little theorem and the rearranging of the formulas that we just saw? 7, which is the element that we're trying to find the multiplicative inverse of in this case, raised to the power of p minus 2. Remember, p is equal to 23 is equal to 7 to the power of 21. Now that's equal to this really large integer value here. But again, because we're operating in a finite field of order 23, we do a modulo 23, which leaves a remainder of 10. So this really large integer value here in the finite field of 23 is congruent to the number 10, proving once again that the multiplicative inverse of 7 is equal to 10. And then the division 6 divided by 7 in this finite field, for example, just becomes 6 multiplied by 7 to the power of p minus 2, or 6 multiplied by 10 modulo 23, which is congruent to 14. Now this might be a bit odd to see something like 6 divided by 7 is congruent to 14, because it's so different from normal math, but once again this is abstract mathematics, and this is the way that we define all of the operations that you can do in a finite field and on the finite field elements in order to make it a finite and closed system, which is really critical for cryptography. Now that you understand how finite field division works, you understand how all of the operations on finite field elements work, addition, subtraction, multiplication, and division, and you understand everything that there is to know about finite fields as it relates to Bitcoin. You can now move on to the next video on elliptic curves, and I'll see you there.